Hi, and welcome to this video where I'm going to show you how to solve for an equivalent resistance in a complicated circuit using Kirchoff's idea of looped currents. So here we have a complicated circuit. It has several resistors and they're not exactly in parallel or in series. So what we're going to do is split up the current into three loops. As you can see here, we have I1, I2, and I3. And it's important to know that I1 is essentially I because it's the first current that will be going through those resistors. So that's important to remember for the end. So our first step is to find an equation for each of the loops. And what I did basically is starting at one point in each of the loops, going around and following the current going through each of the resistors that it passes through. And you need to find what current, or exactly the net current, that's going through each resistor for that loop. And so that might mean that it's negative or that it's positive. So for example, going through the first loop, we have a positive I1 because that's a drop, and a negative I2 because it's a climb in voltage. And so we're calling that I1 minus I2 that's passing through R1. And you basically do that for the rest of the resistors for each loop. And since we're coming back to the same point, the voltage drop, or the overall V, will be 0 for that loop. So you have V equals IR for each one. So for the first one, we have I1 minus I2 equals R, and then I1 minus I3 that's going through R4 minus V naught because we're climbing that voltage of V naught. And then for the second loop, we have I2 times R2 plus I2 minus I3 times R3 plus I1 minus I2 R1. And then the last loop, which again is equal to 0, is I3 R5 plus I1 minus I3 R4 plus I2 minus I3 R3. And if you need to pause and take a closer look, really the important thing to remember is that you have set out what is a voltage drop and what is a voltage climb, and you keep those constant throughout this entire problem so that you don't get mixed up for each loop. So our next step, basically what I did is just rewrite those equations so that we have the I's and then the resistances that go along with them, but you don't really necessarily need to do that. But our next step is to get I2 and I3, solving for them in terms of I1 and another I3, because remember, in the end, we only want I1 since that's the I that will go along with our equation V naught equals I1 times REQ, and we're looking for that REQ. So I took these first two loop equations. It really doesn't matter which ones you use, just as long as you're not solving for an I2 or an I3 in one equation and then plugging an I3 back into that same equation. If you just used it, then you'll just come up with nothing. You need to use a different equation for each I. So we used I2 for the first one and just solving out for that. So it's in terms of just I1 and I3, and then using the second loop equation and solving I3 in terms of I1 and I2. And our next step will be to plug that I3 into the first equation, I2, and then vice versa. So we come up with an I2 and an I3 that are only in terms of I1, and you will see how that is helpful in a little bit. So now that we have our I2 and I3 in terms of only I1 or I2 and I2 or R3, I'm going to take the equation for I3 and plug it into I2 and solve for I2 again so that we have I2 only in terms of I1. So if you go back, you can see that all I've done here is just plug in I3 into this equation, and then I'm solving out for I2, and we get this lovely equation for I2, which we can see is only in terms of I1 and our known resistances R1 through R5. And it's not very pretty or neat of an equation, so we're going to simplify it for now using constants, so that I2 is equal to I1 times Z, and that's just a random letter that I'm picking that isn't used later on. You can say it's anything you want, but it's important to record exactly what that Z is because you're going to need to plug it in later, but for now we can keep that as I1Z minus V0G, which again is just another constant to replace the not so pretty equation going on there. So we have I2 equals I1Z minus V0G, and our next step is going to be doing essentially the same thing for I3, where we're going to take the I3 equation that we have, which is currently in terms of I2 and I1, and plugging in that I2 equation that we had before so that we get an I3 that is only in terms of I1, and this will again help us in a second. So here we have our I3 equation, and again I'm just plugging in the I2 that we got from that first loop, I think it was, into this I3 equation so that we have I3 and I1 as our only unknowns. And now just going through the process of solving for I3 again, so that it's only in terms of I1 and these R's that we already know, and that comes out to this equation for I3, which we can see is only in terms of I1 and again those known resistors that we have, and like the I2 equation that we had, it is not very neat, so we can do the same thing as before and replace some of the less simple parts of it with constants, so we end up with I3 equals I1 times Q minus V0 times W, and again those are just random letters that I'm picking, but it's important to remember what they stand for because we're going to need that in a second. So now we have an I1 and an I2 that are only in terms of I1, and our next step is to plug in those I3s and I1s into that final equation that we got from the third loop that has not been used yet. Remember again that we can't use the equations that we've already used, because then we'll just end up with something equals the same thing, and that's not helpful at all. So we're plugging into that last equation, and I've written it at the top there, and it's pretty simple, just keeping it in terms of those constants for now, so that we end up with an I1, and it's only going to be in terms of I1 and the R's. And remember that that I1 is the I1 that we need, or is the current that we need in our equation V0 equals I times Req. That I is the same as I1. So as soon as we can solve for I1 definitively, we'll get our Req, and that's exactly what we need. So if we remember our equation V0 equals I1 Req, we can write that as Req, which is the equivalent resistance we're looking for, equals V0 over I1. And if you need to go back and look, we can see that I1 is a fraction, so if we're doing V0 divided by I1, we could just say V naught multiplied by the reciprocal of I1, and that's going to come out to this equation here, REQ equals, well, you can see it, and luckily those V naughts cancel out, so which makes sense because the voltage should not affect the resistors at all. So our next step is the final step, and it should be pretty easy. We're just plugging in those constants for what we had before, and it's not going to be pretty, but it's going to give us our equivalent resistance. Here we have our final equation for equivalent resistance. Yay! And like I said, it is not pretty, and we can see that that final step was just plugging in for the Q and the Z and the W and the G that were already determined, and just doing it at the end makes it so much easier. You don't have to keep writing out all that stuff through the entire process. And clearly we could not solve for this complicated circuit equivalent resistance without the help of Kirchoff's law, which just goes to show how helpful it is. So thank you, Kirchoff, and hopefully you learned something about circuits and how to solve for an equivalent resistance. Thank you.